Howdy, friends. So the long overdue lecture going to be a short one, but it'll get us ready for Monday. Um, Let me just get right into it. We've been working on Runge kutta methods for first order one-dimensional differential equations. And what I want to do next and last is to move this into higher order differential equations. And also, then how do we deal with those? How do we use the Runge-Kutta methods to deal with those since they're only first order methods? And the trick is going to be to take our higher order differential equation and convert it into a system of first order equations. And then we're going to apply the RK methods in a very natural way, essentially to each dimension of the system. So let me just grab a sip of coffee and get rolling here. I want to start off motivating where a higher order system could come from instead of just putting an equation on the board here with second, third, fourth derivatives in it. Let's get a concrete example. And then on your final exam, again, a take-home exam, you're going to analyze a related system to what I'm about to lay down here. So let's start off with my favorite example of a higher order system, and that is a mass spring system. What does that mean? Well, we need a new color. So here, this is like some sort of support on the ceiling, and then I've got a spring that hangs down. And at the end of that spring, I have a mass M. And what we're going to do is we're going to study the motion of that mass M over time. Uh, After we do different things to it, we might pull it down and release it. We might push it up and shove it down at the same time. We might possibly put some kind of damping in it. So uh, immerse this in water and watch what happens. And, we're not going to, but we could externally force this thing with some kind of additional force being added to the system. And we're probably not going to get there. We don't have all that much time left. So let's just look at the basics. So first off, I've got this spring. And we're going to assume we have what's called a linear spring. Now, a linear spring means that if I want to move the spring, I want to extend or compress it by X units, then that the force required to do that extension or compression is given to us by what's called Hooke's law. So if I let's say we're in KMS system, kilograms, meters, seconds system, and I've got this particular spring here, and I want to extend it. I want to pull it down, say like 2 meters. Then the force required to do that is going to be governed by this equation right here, and that K is a constant. That should be a 2 there. The larger that K is, so 2 times K, because our mass is 2. Um, put meters here so it doesn't look like mass. the larger K is, the stiffer the spring is. It requires more force to move it a particular number of units. So, for example, if K equals 1, then this requires 2 units of force. I want to say newtons. I guess I did just say it. And if K equals 10, then it requires the force is 20 newtons required to do that same extension. And of course, the smaller, when I start getting into fractional Ks, then we have a looser spring. So imagine some floppy spring versus a very stiff spring, like the spring on a car suspension is terrifyingly stiff, finger crushingly stiff. So we're going to assume we have a linear spring. Now, that's probably not a reasonable assumption if we're going to be doing large extensions or just a reasonable assumption in general. But for small perturbations about equilibrium, so for small extensions or compressions, we could assume that the spring is linear. We're going to assume it's linear no matter what, and we'll still gain some understanding here. All right, so let me flip pages here. So I got my spring and I attach a mass M to it. Now, currently, there's only one force acting on this thing, and that is the force of gravity. And gravity, or the acceleration of gravity, gravity is, we're going to say, not assume 9.8 meters per second squared. So I said the force, the acceleration of gravity pulls upon that mass and creates a force. You know, I'm not a physicist. I've taught calculus a lot, taught diffie-q a lot. So if any of the things I'm saying offend you, I beg your forgiveness. So what we're going to do, let me get rid of that, is we're going to take this spring, and what we want to do is come up with an equation of motion for this thing. We're going to assume there's no friction on the system. That translates into no damping if in the language of mass spring systems. But right now, we're going to assume that this spring, if I take it and let's see here, hold on. We're going to say the spring has length L. So right here, with nothing else happening, hold on. Oops. Backing up. Gonna back up. Apologies. I gotta admit, I'm kind of winging this from memory. So I gotta slow down a little bit. Here's my spring. Now look, it's green. The, you know, nice appropriate green. So the length of the spring itself is just L units. There we go. And then I'm going to attach the mass to it. So the spring, without any mass on it, without any force being applied, is L units long. Next, I'm going to get blue. I'm going to draw these side-by-side pictures. I'm going to attach the mass to it. And that's going to pull the spring down a little bit. And how much did I pull that down? Well, let's make a little line across here. Let's say that when I attach that mass, it pulls the spring S units down. So this distance to the center of the mass is S units. So right now this whole spring is S plus L units long, and the system is at equilibrium. And it's from here that we're actually going to get our equations of motion. But let's stop for a minute and look at the forces acting on this thing and get an important equality that we're going to need a little bit later. And let's do that in purple. So what is happening here? What do we have acting on this spring? Well, we have gravity. this mass is accelerating toward the center of the Earth with the force G times M. And what I'm using here is Newton's second law or something like that. The force is mass times acceleration. It's one of Newton's laws, right? So we have the acceleration of gravity G and the mass M, and that is pulling down, creating this downward force on the mass. And simultaneously, the spring is wanting to restore upward. So I have this upward force on the spring. Now, what is that upward force? Well, I've stretched it S units, and we're assuming that Hooke's law here is in effect, and this spring has a certain stiffness denoted by K. And Ks is the force acting upward, the amount we've stretched the spring past its natural state. Right now, this mass is still. It's just kind of floating there in the air. We're assuming there's no motion. And what we've got then is these forces in balance so that Ks equals mg. Let's denote that here and come back to it in just a few minutes. Now I'm going to do this whole picture again down here. So now we've got, so I'm extending it. So we've got the spring and we've got the mass on it, but now we're going to assume, well, actually, let's just copy that picture down again. So there's M, and here's that equilibrium line across there. This distance here is S. This distance up here is L. That was the natural length of the spring. And now I'm going to grab the spring and let's just assume I'm pulling it downward a little bit. So pulling it past this equilibrium state. Let's put that picture right next to here. So spring stretched out a little. Great spring. Huh? Get your money back on that spring. It's pretty weak. So now what we've done is we've pulled this thing away from equilibrium. And let's get another line. We're going to call that extra stretching X. We're going to assume that when I pull downward, this is X positive. And if I actually compress back up so that the spring moves to a shorter state, so imagine this mass over here to the left, coming up above that purple dotted line. So this up here is going to be X less than 0. So again, X greater than 0 is extension, X less than 0 is compression. And let's analyze the forces that are acting on this system right now. So again, Newton's law not only allows us to analyze, to find the force given the mass and the acceleration, it also helps us to relate acceleration to the forces applied on a system. So you take something that's at equilibrium, you apply a force, acceleration is produced in proportion to the mass that is being acted on. So let's just get some black here for a second. So if X equals the extension, let's just say position, then dx dt, which is x dot, is the velocity, and x double dot, see now we're getting a second derivative, that's Second derivative of x with respect to t, that is the acceleration. So I can come down here and I could say, well, that the mass times the acceleration that's produced by the state that we're in, all the forces acting upon it. So this is x double dot is our acceleration. Again, this is ma right here, is going to equal the sum of the forces acting on the system. What is acting on the system? Well, we still have gravity, and that is mg acting in the extension direction. In other words, downward. That's our positive direction. But then we have the restoring force of the spring. So put that here. So right now I've got mg pulling down, and then what I've got is the spring force pulling up. And what is that going to be? Well, it's k times the extension past the natural state of the spring. Well, that was an s plus, so this distance here, that's s, plus this additional x. And that is acting upward. So I'm going to subtract that down here. I've got k times s plus extension past our equilibrium position. So check that out. I've got this nice equation down here now that relates the position of the mass to its acceleration due to the forces acting on this system. All right, so let's move to a new page here real quick and copy that. I've got mx double dot, we've kind of got past the hard part here, equals force from gravity minus restoring force of the spring. Ooh, wait a minute. Did I miss a force? Let's go back here. Oh, page back is what I want. Yes. Yep, we're good. Okay. Just wanted to make sure everything was in order. So this was S plus X right here. Let's do a little work. So we've got mx double dot equals mg minus ks minus kx. And this looks messy, but we've got this sweet thing here. Remember that at equilibrium, mg was ks. The force of gravity was equal to the restoring force of the spring, and nothing was moving at that point. Everything was in perfect equilibrium, perfect balance. So that means these two quantities cancel each other out, and I've got mx double dot equals negative kx, and usually we pull everything to one side, and so I've got mx double dot plus kx equals 0. And now we see our first second order differential equation. And there's some initial conditions that come with this. We can say x at time 0 is the initial extension. That's how much I pull it away from equilibrium or compress it. If this quantity is positive, that's an extension downward. If this quantity is negative, I've pushed the spring up past equilibrium. And then we have x dot at 0 equals the initial velocity. And that means I've given the mass either a shove upward or a shove downward to get things rolling. And now we have our first mass spring system. Again, there are two initial conditions that come with this. So remember that this is the velocity at time 0, that x dot. Cool. So one thing we could do is we could actually incorporate some damping into this, and I kind of want to do that. And on the next page, over here. So again, let's look at what our net was here. We had mx double dot, the ma, the force, the mass times the acceleration, the total force on the system. At the current moment, we had this. The only thing really contributing to the acceleration in the system was the spring force, because everything else balanced out. But I might also have a damping on this. And I'm going to toss this in here as a minus mu x dot, and then I'm going to talk about it. So this is a linear friction term. So the mu is equal to the damping constant. And the x dot again equals the velocity. Notice that that is acting in the opposite direction of the acceleration, because damping will always slow you down. It's kind of always working against whatever direction you're trying to accelerate in. Think about this analogy. You're walking through a swimming pool, and just imagine this, you may be up to like chest high in water and you're just walking along the bottom. What happens when you try to accelerate? Well, the faster you try to go, the more force you feel pulling against you, the friction force. But if you keep walking slow, it's pretty manageable. So that's why you see people walking along the floor of the pool very slowly, right? Just picture some person out in the pool just walking slowly, because when they try to accelerate, when they try to go faster, um, it doesn't really work. You just feel all the force of that water pushing against you. So this is our damping force, that mu x dot. And now our full system is this. I'm going to get everything to one side. Again, we have initial position, initial extension, and x dot at 0 equals initial velocity. And we're going to stop here in terms of developing this system. But you can think of this system as a very simple model of any sort of sinusoidal activity. So any sort of system where wave activity is expected, you're going to see this type of equation manifesting when we model it with differential equations. Cool. Now, I'm not going to go through the whole theory of solving differential equations. Not at all. Suffice to say that this system has a solution that kind of looks like this. If we were to go through, we'd have some arbitrary constant times E to, and now there's going to be some, these numbers, these have to, I don't quite know the exact relationship between that K that I just wrote and the mu. Nope, I don't want to use K because there's a K up there. How about we just say, let's pick a cool Greek letter, let's say nu t. So that's e to the negative nu t, cosine of, and then we're going to have some frequency term omega t plus c2 e to the negative nu t sine of omega t. So that omega is the frequency of the system. That's something we can use to determine how long it takes for a full period of the mass. In other words, if I watch this mass cross equilibrium, how long does it take to come back to equilibrium? So maybe it goes down, crosses equilibrium, goes up into compression, and then comes back down again to equilibrium. I could use that omega to decide how long that takes, to determine how long that takes. This e to the negative, what the fuck did we call it? New. I don't know. I guess I called it new. It looks like a V, whatever. Um, so that term right there is creating an envelope. Think about what e to the negative t looks like. Looks like this. So you see that decay happening there. And what happens is that creates an envelope for the oscillations, and you see the sine and cosine stuff getting damped out. Well, that looked really bad. So now I gotta go. That's more realistic. That's, there's friction in the world, both in physical systems and in our lives. But we see things die out, things lose energy. And we watch that thing oscillate, but inevitably come back settling at equilibrium, unless there's some sort of external energy being applied. We're not going to think about that. Okay, so can't use Euler's method, can't use any of the Runge-Kutta methods with a higher order thing until we convert that into a first order problem. And on Monday, we will talk about how to deal with first order problems, and I'll have some code for you. I'm not going to have any code for you today. I just want to prime our brains to be ready to talk about this stuff. So let's put that dude back up here. So I've got mx double dot plus my damping plus my spring force. Those all add up to 0. And then I've got x naught at 0 equals, just say x naught, and woo, no x dot. Why did I put a dot there? X at 0 equals x naught, and x dot at 0 equals initial velocity. So I want to convert this into a system of equations, two first order equations that are woven together in such a way that all this information is encoded. And the way I'm going to do that is I'm going to introduce a new variable, and I'm going to introduce a new color to do that as well. And the key here is that we know that the velocity, so that's going to be my new variable, v, is equal to the first derivative of x. So again, I'm introducing a new variable, v. And I've got now a system in two variables, x and v, position and velocity. Well, if velocity is x dot, and I want to convert this thing, oh, this thing is a piece of, this software is garbage. It's been nothing but frustrating. And I paid for this shit. Unbelievable. So, what is v dot? We're going to have a differential system here. What is the velocity's rate of change? Notice that is the acceleration, the rate of change of velocity with respect to time. But v double dot, if I just take this equation right here and I differentiate it on each side, I get that that's equal to x double dot. What does x double dot get? Well, I can take equation star and solve that for x double dot. So by equation star, we'll do this a little bit slowly. First thing I've got x double dot equals negative mu x dot minus kx. I'm going to divide both sides by m, and I get x double dot equals negative mu over m. M is positive. All these constants are positive. I haven't said that, but they are, minus k over m x, and I lost my x dot right there. And now I can plug this in. So x double dot, that is actually v dot. That is the rate of change of the velocity. So it's v dot. I want to introduce my new variable, equals negative mu over m, some constant, times x dot. And x dot is v. minus K over M X. So take this equation here, and I'm going to actually bring down this starred equation up here and put it underneath what we've got. So hold on, let me clean up. So I've got X dot, there's one of my equations that relates X, V, and the rate of change of X. And then I've got this original equation that I introduced, and that is that, oh shit, sorry, sorry, didn't mean to be confusing. This is X double dot right here. So that is V dot. There we go. So V dot equals that stuff to the right. And then I introduced this original equation that said X dot was V. Now I've got a system of equations. You're going to get a chance to do this in a very simple situation. Isn't that exciting? Might even want to come back to this and just kind of hack this into what you need when you need it. So what are our initial conditions? Well, we had X at 0 is X naught. We're still having that equation, that initial condition. But then I have X dot at 0 is V naught. But X dot is V, so I have V at 0 equals V naught. And now I've got a first order system of equations, and it represents that second order equation. Now, the way this generally goes is if I had had a third order equation, so something with a third derivative in it, I would end up with 3 equations, each of the first degree. So you can use this method here to convert any higher order system into a lower order system. And the trade-off is for each derivative level you want to represent, you need another dimension in it. We're not going to go past second derivative and aka second dimensional system. But I think we kind of, I want to say one more thing here. I want to just at least talk about how we could represent this with matrices. So let's see, how do I cut and paste some stuff here? Let's try this. To copy it, oh, look at me. And then I'll come over here. Oh, I did it. Unbelievable. And there's just some garbage that came along with it. Oh, that's so much better. Okay. And then I had these initial conditions. I'm just going to put them up here at the top that X at 0 was X naught, V at 0 was V naught. So I can actually turn this into a system that is represented by vectors. And my vectors are going to have 2 components, X and V. So all my solutions will be vector valued. And to say that I want the derivative of that vector, this is just this left-hand side over here. So that dot above the vector means apply the dot to X, apply the dot to V. And on the right side, I'm going to have a coefficient matrix, a constant coefficient matrix, and I'm going to have that times X, V. So when I do that, probably you want to think of these two in flipped. So I've got the X dot equals V on top. And if I wanted that, think about having a row of 0, 1 in this matrix. So now look, left-hand side, I've got X dot equals 0, 1 dotted with XV, and that just gives you V. Just think matrix multiplication, row dotted with the column. And then in the bottom, I've got negative mu over m. Nope, the x is first. Oops. So I've got negative k over m, negative mu over m. And I got myself a nice old system here in matrix notation. So this represents the mass spring system. Let me give you an indicator here. I don't have any code ready yet. I'll have that for Monday. But let's just really talk about what we would see in a system like this. So let's say I had a simple mass spring system. We need all new colors. All new colors. Dark blue. So for example, let's say I had x double dot plus 4x equals 0. I had x at time 0 is 1 and x dot at 0 is 0. Now I'd like you to take a minute and just see if you can picture what's happening here. First off, note there's no damping because there's no x dot term. So this is an undamped mass spring system. I have an initial extension of 1 unit, so I pull it down 1 unit, 1 meter, whatever, some fraction of meters, more than 1 meters, the big ass spring. And I have no initial velocity. So I've taken my mass spring system, which hangs like this, there's M, and I've pulled it down 1 unit. So I pull it down 1 meter. I release it. What do I expect to happen? Well, I immediately expect it to rise back up past equilibrium, compress the exact same amount that I extended it, because the energy is not dissipating from the system, move back down through extension, reach the maximum extension, come back up. This maybe is equilibrium right here. Come back up, compress, come back down. So from this, I can see that system, but let's take a look at the 2D version. So here's T and here's X, your extension. And I started at 1 unit of extension. And then the period on this thing, we could figure it out, but let's just play loose with that for a minute. So this is the behavior of the extension of the mass spring system as time moves on. My God, what the fuck is that? Oh my God, bro. Okay, there we go. Just give me my pen back. Thank you. Extension. So remember that negative down here, this is the compression. This is the extension up here. And that t-axis is equilibrium. We continue to do that. There's no damping. The system just oscillates forever. But what if I think about this in terms of 2 dimensions? So now I've got x, which is my extension, and v, which is my velocity. This is going to look completely different. And the time variable is hidden in here. The time variable manifests as the motion of a particle in this plane. So we started off with an extension of 1 unit. Let's get a new color. Let's get nice pink with purple. I started off right there. This was 1 unit of extension, no velocity. Now what's going to happen? We're going to see x. Oh, it's right above me. We're going to see the x coordinate decrease. And the velocity is going to increase. Right now we have 0 velocity when we release this thing, but the spring is going to pull up on it and it's going to reach maximum velocity as it crosses equilibrium. And then it's going to start to slow down as the spring begins to compress again. And then we reach maximum compression. So x is decreasing, velocity will increase until I reach equilibrium. And so that means I'm going to see a movement like that in this particular particle. So like right now at that moment, this is equilibrium, crossing equilibrium. Because x is 0 at this point. What is the coordinate there? It's x is 0 and then v is whatever. We don't exactly know what the velocity is. Maybe it's 1. Maybe this is looking like a circle. But it doesn't necessarily have to be. This could be an oval. Maybe we're going a little bit faster than 1 unit per second as we cross equilibrium. And then what happens? Let's actually do this in multiple colors on that graph. So next, orange isn't a good contrast, just do yellow. So now I'm at maximum compression and I start to extend again. And so this little piece right here is max compression at the bottom, no motion, no velocity. You're stopped for an instant when you're at those ends of the extension or compression. And then at your zero velocity, as the spring starts to push back down, you gain velocity. You gain maximum velocity as you cross. Oh, my yellow is maybe not a great choice. Maybe orange is better. So right at this moment, I've got maximum velocity as I cross equilibrium, and then I start to slow down again as I extend, and the spring starts to pull back on me. It's diminishing my kinetic energy and turning that into potential energy as I reach maximum extension. So that little orange piece up there looks like this down here, and I reach -1 on the X position. Now this again was max extension. This is max compression. Hold on, I think I said that as backwards. Let's see here. Close that up. Let's see, so X goes from 0. Yeah, I kind of screwed it up. Sorry, I'm gonna redo this. Let's look at those two pieces of motion up there on top. Sorry about that. But we'll use those colors we have up here. So we start here. This is X. This is velocity. X starts at 1. Velocity is 0. Let's call these points A, B, C, D, and E. So when I'm at A, this is point A right here. At B is we have X is 0, and we're at max velocity. So that's actually right here. And we're moving like that. X is decreasing, velocity is increasing. Then as here we go. Then as I move from B to C, I had it like halved. As I move from B to C, now I'm at -1. And that's max compression. And then this whole thing now, so that's the pink arc up there. Looks like this. And then the orange arc is I move from max compression, crossing equilibrium again. So this is point D, moment D right here. And then we move all the way back and we've made a full cycle. As I come back, this is D, and then A and E are the same state down here. They look different up there because we're watching it over time. So in this plane here, the XV plane, what I see is this circular motion over and over again, watching the interplay and exchange of velocity and position throughout the system. Again, time is hidden here. We are simply watching this particle spin around here. And that particle is a bit abstract because, again, it represents position versus velocity. So this is more intuitive up here. And this is a completely different perspective that gives us a deeper insight into that interplay. So that's all I got for you. That's probably enough. I'm going to put a little note at the top about that part that I hosed up. So hopefully you'll read the notes before you get there. And that's it for today. So please, I'm going to coax you to watch this in some way. I'm going to put a little thing here in a different color. And if you send me an email with this, I will give you some bonus points. Now, this was going to be an assignment, but I did it so freaking late that I don't feel that's right. So I'm going to write something in pink and just send me this word in an email. So just go for king. That's the subject line. Don't have to say anything else. Send me an email with that before class on Monday. It has to come. Otherwise, I need you to watch this before class on Monday. So an email, go for king. You can space that or not. I don't know. You choose. So it's go for space king or just go for king in your email subject line. And just do that before class, and I'll give you some bonus points on something. I don't know what yet. Just kind of making all this shit up as we go. So that's it, my friends. Thank you. I hope you had a good break. I hope you and your family and your friends or whoever you were with got along. I hope if you were alone, you're okay. And if you need anything, please reach out. And I will see you very soon. So at this point, I just have to figure out how to shut down the Zoom thing. All right, I'm going to pause this.